Okay, so next we'll move on to our last talk of the session from, and I apologize if I get this wrong, Jinyi Shangguan from Max Planck Institute of Extraterrestrial Physics on spatially resolving the inner parsec of AGN with gravity.
Thank you. I hope you can hear me. So I will.
Yes, we can hear you and we can see your screen, but
okay.
It's the small version. Yeah, there we go.
Okay, thank you very much for the introduction. Yeah, hello everyone. So my name is Jinyi Shangguan. I'm a postdoc in MPE, and the talk is on behalf of the Gravity Collaboration. So I'm very grateful that you give me this opportunity to talk about our gravity observation of the AGNs and supermassive black holes outside the Milky Way. We'll also end up the talk with showing you some preliminary results that demonstrate the power of Gravity Plus. So all of the results come from the great teamwork from the Gravity Collaboration. And here I show you some of my colleagues who are closely involved in the data analysis and interpretation of the AGN observation. So yeah, so in the beginning of this session, you've heard two talks about the great discoveries in the center of the Milky Way. We strongly believe that there is a supermassive black hole there. And in fact, we now know that the supermassive black holes are prevalent in the center of all the massive galaxies in the local universe. We can probe them from the stellar dynamics or the dynamics of the gas. In the distant universe, we can actually find luminous quasars. In fact, these quasars are one of the first evidence of this existence of this supermassive black hole. And after the discovery, astronomers push the discovery of the quasars out to more and more distant universe. Now the quasars are found above redshift 7.5 and well within this regime of reionization. How do those black holes form and how do they quickly grow their mass is still a very big puzzle. And also when the black hole grow their mass, they evolve in the accretion with huge energy release. This is believed to affect the evolution of the host galaxy. All of these are the big questions that we want to understand in the modern astronomy. And these questions, these discoveries are possible because we can measure the mass of a supermassive black hole. And although it's quite uncertain, but I think this is a very great achievement that you can even measure the black hole mass with a single epoch of the spectrum. You measure the line, the broad emission line, the line width, and the luminosity of the AGN tells you can estimate the mass of a black hole. You can actually measure this black hole in the quasar out to very high redshift. Of course, these measurements, these estimates are quite uncertain because they really rely on the calibration in the low redshift local universe. This based on the so-called reversion mapping technique. The methods use the time lag between the variability of the emission line from the borderline region and the continuum to resolve the size of the BLR from the time domain. And you measure the variability, so really very time consuming and not easy to be applied into a high redshift universe. And we have to rely on the time because, the BLR is so small, like the spatial scale, like 10 to 100 microarc seconds. So it's not possible before using a single telescope or even with ALMA or the other radios and millimeter interferometers. It has been only possible recently with gravity. We can spatially resolve the BLR in the near infrared. So this is the first target we can resolve the BOR. Actually, exactly the first quasar people discovered, and our observation comes from the broad partial alpha line redshift into K-band where gravity observe, and the key measurement is the so-called differential phase. I don't think I need to explain too much. We see this kind of S-shape signal tell us the photocenter of these channels dominated by the light emission offset from the center of the continuum, like this cartoon shows. You can derive that the differential phase amplitude is proportional to the strength of the line and also the photocenter offset project to the baseline. And because we have 6 baseline from VLTI, we can actually solve the equation for each of the channel and reconstruct the photocenter. We find that actually the photocenter is perpendicular to the jet to be rotating around in this direction. This is purely a model independent method. And if you want to measure the black hole mass and the size of the BOR, you need some dynamical modeling. So it's possible to do it. And with the success of 3C273, we actually start a large program with gravity to observe a few more bright AGNs in the local universe. And up to now, we have another 2 measurements published, and we are working on a few more sources. We tend to see this radius luminosity relation of the BLR, and you see this actually the regression mapping results seems to be consistent with our measurements. And the RM and the AGN large program also bring us the hot dust measurement. So we can actually, so for the type 1 AGNs, they are mainly marginally resolved. So we can actually measure the size from the visibility drop. Most of the source, they do not show strong closure phase except for one. And the dust continuum size also follow the luminosity. Up to now, we already observed more than 10 objects. This seems to be quite consistent with the previous observation from either the regression mapping, also the interferometry. I don't want to spend too much time on this because I also want to show you the nice image from the prototypical type 2 AGN, NGC 1068. This is a very nearby source, so gravity actually fully resolve it. And from the reconstructed image, we find a ring-like structure and seems like a thin disk. And because we don't have absolute astrometry, we need to align the peak of the emission according to the radio in 22 gigahertz. And after the alignment, we find that actually our disk seems to very well coincident with the maser disk. And this brings me to strongly incline that the black hole seems to be in the center of the ring. This is a very interesting result, and actually even more recently, Matisse also showed the observation in the longer wavelength. They also find disk-like structure and also with this kind of elongation. Overall, this image seems to be quite similar. There are some complexity coming from the astrometry. As I said, we don't have absolute astrometry in either of the observation. I believe we will have more discussion in the talk later today from Violetta. Yeah, so I will continue. So up to now, I mainly talk about the results in the low redshift universe for the bright source because we are mainly limited by the phase referencing. And we do want to push the sensitivity so that we can observe a lot more AGNs with fringe tracking higher fringe tracker sensitivity and also the wide angle phase reference. This will allow us to probe the black hole beyond the cosmic noon. And with Gravity Plus, there are actually a lot more important science goals, but I don't have time to go into the details. I want to advertise Matthew's talk tomorrow morning about Gravity Plus upgrade, instrumentation upgrade. And now I would just want to emphasize that gravity, this wide angle phase reference, Gravity Wide, has been already commissioned and will will be available in P110. And during our commissioning, in order to test the sensitivity of gravity-wide, we actually try to observe 2 Redshift 2 quasars. These are very exciting observations. We can actually clearly detect the coherence flux from this quasar, and especially for the second one lower, the signal is quite strong, and actually we believe we already see the S-shaped differential phase signal. This encourages us to do more modeling, and I will show you in a minute the results. I want to explain why we want to directly go to Redshift 2. Although the quasars are faint, the H alpha line redshift into K band. So the line to continuum ratio is much stronger than the other lines, as you can see. And also the quasar is actually are the most luminous ones in the universe. So the BORs are huge. And also the redshift broaden the line, so we have more channels to detect the differential phase. All of these help us to detect the differential phase signal of the BLR. And for the second source, even though we only have about 1 hour exposure, we can actually reconstruct the photocenter. Although the different channel, you see the position, the photocenter position show relatively large uncertainty as shown in the ellipse. You can clearly see that the blue and the red show very clear offset. On average, their separation is quite significant. This encourages us to do even more dynamical modeling. And we find that we can actually constrain the BLR size, geometry, and the black hole mass. If you put the BLR size to the RL relation, our result, you see, tend to follow a nice trend. Of course, there are too many gravity points, but you see here also good consistency with the regression mapping result. You see that the size of a BLR below this previous early RL relation from the low redshift universe. I think this is actually physically quite interesting, probably tell us and confirming the idea that with black hole with high accretion rate, the BLR size may be smaller. Yeah, so with this, I would like to summarize my talk. I show you how we spatially resolve the BLR. And with a large program, we already observe quite a few targets and have some nice results, and very exciting. We already see the breakthrough with gravity wide for these Redshift 2 quasars. And with this, we are very much looking forward for the full power of gravity plus. Thank you very much. And I'm happy to take the questions.
Yes, are there any questions for Shangguan? Anybody online? Okay, then I have a question for you. In your plot, in the corner plot on the previous page where you were modeling the Z equals 2 quasars black hole mass,
yes.
Is it really accurate that you managed to get to 0.3 dex with an hour's worth of exposure? Is that something you think would be common, like you could do on multiple objects, or is it just this is a particularly bright and easy source?
Yeah, this source is definitely one of the brightest sources in what we can find. That is why we use this to test for now. The modeling with the number, so these are still quite preliminary modeling, but I think this is not so this is not too much surprising. As I explained earlier, you see the phase signal is quite significant. And here I'm showing you the binned data points. Actually, we have more data points to constrain the data. Yeah, I would say that we are not, I think it's good to put in this way. The results are quite promising, and we do see you see here actually the size is about like 2 sigma significance. So we do see very promising result to resolve the BLR, but we hope that we can have a few more hours really to pin down the detection. Yeah, does that answer the question? Thank you.
Thank you. Anybody else have any questions? Yes, please go ahead.
Yes, Stefan Cross, Exeter. There was a paper by Sebastian Hönig a few years ago and colleagues about combining reverberation mapping with the angular size measurements from interferometry. So where is basically the sweet spot for that technique? Do you think that is also an important science case for Gravity Plus, or how many objects could you get meaningful distances with that technique?
Oh, thank you very much for the question. Yes, indeed, this is one of the science goal for our AGN science. I just really don't have time to talk about that. Actually, in terms of measuring the geometric distance, there are actually two ways. One is using the dust continuum. The other is actually just use the BLR itself. Both methods, I think it's they are all very promising for the dust continuum because we rely on the so for the dust continuum we rely on the our accuracy is relying on the visibility amplitude to measure the continuum size. So we cannot go to super high redshift. So the sweet point for the dust continuum method, I think, is within low redshift, but with this partial alpha Bragg gamma sources. Yeah, if you go to very high redshift, the continuum we don't see firstly the dust continuum redshift out of K-band. So for example, the redshift 2 quasars, we see the continuum from the accretion disk. So that's different. But if you go to higher redshift, these we can try to use the BLR to probe the geometric distance. This is also not very easy. So when you go to high redshift, as I said, the BLR become quite large. This is good for, sorry, I should go here. The BLR become quite large because the AGNs are huge, luminous. The BLR become large, but it's more difficult for reversion mapping to measure the variability because everything takes longer time and you multiply by the redshift 1 plus z, so it's even longer. But this could be done, and I think it's quite promising actually.
Okay, thank you. Any final questions before we take the break? No, then thank you very much for your talk.
Thank you.